what are the challenges and the limitations that one faces while doing some field testing? We'll look at how simulation can be a very viable option for doing electrothermal applications. And then bulk of the time we'll be spending in product demonstration, where I will be showing you our EMS product and one application for electrothermal. And then we will spend the last part in introducing our product bundles, talking about few application areas, and also answering some of your questions. Let me start briefly with what are the challenges engineers face in the electrothermal application area. Okay. First of all, if you look at components and devices, they've all increased in their ratings. You know, their capabilities and their performance are being enhanced, or the demand for those things being enhanced are tremendous. Okay, and simultaneously you feel a pinch for the devices getting smaller. So there is reduction in size and reduction in weight, but at the same time the performance has increased or can never be compromised. Okay, this is a dual challenge that engineers face all over the world in this particular application. Okay. And they also would like to get an understanding of an accurate performance of their devices and also the prediction of their losses, any type of losses that occur. This might include the accurate prediction of thermal behaviors, okay, because temperature and heating, they form a very critical component of the design, and most of the failures could occur due to a rapid temperature increase or temperature increase beyond a particular point. Okay. And obviously for people who probably design machines, electrical machines, where induced current is of concern, one would like to reduce the eddy current losses, and for designers and users of transformers and those type of devices, core losses also need to be reduced. And finally, one needs to identify the hotspots in one's design, and also we would like to try and eliminate some of these hotspots from critical components. Let's take a look at some of the limitations of physical testing. Here I have a transformer design here over the left, and you can see some of the small thermal sensors that are being stuck onto the transformer, and here are the locations of the thermal sensors, and you can see the intricacy and the design challenge that just a very small part of the transformer interior is being shown here. So obviously some of the limitations are quite obvious when I take a look at a device something like this. Okay, what are they? Okay, first of all, these kind of sensors and testing equipment, obviously the whole setup and testing requires a lot of time, a lot of effort, and obviously a lot of expense, right? The second challenge, which is more obvious to the picture that you saw, is there's actually a physical limit to the number of sensors that one can possibly have. Okay. And the third challenge here is, how do I predetermine the location of hotspots? If I'd known that these places would get hot, then I would place sensors there. But sometimes in new designs, and especially when you're coming up with new product development, you don't know really where those hotspots are going to be to begin from. So it's really important for you to understand them, but while doing physical testing, it's almost impossible to accurately detect where they are, because you're not going to have a sensor in almost every possible point in your model. Okay. And finally, how does one measure losses using physical testing? It's always a challenge. There are devices and equipments and standard procedures, but ultimately it's highly limited. And now that leads to a very interesting question: why simulation? How simulation can help you overcome some of these challenges? Okay. First of all, simulation can actually help you visualize the complex electromagnetic field inside your model. Okay, it's practically impossible because electromagnetic fields are not visible to the naked eye, so you would not be able to visualize them through any testing procedures. Okay. All you will get is a few data points in various locations, but a complex 3D electromagnetic field visualization is possible when you do some kind of simulation. Second is all types of losses, for example, ohmic losses, core loss, etc. They're all computed. Simulation computes them as an output quantity. Third, simulation helps you to visualize the temperature field. Okay, the temperature distribution across a model. You can look at temperatures inside a model, at the periphery, and so on. Whereas if you were to place sensors, you're pretty much limited to probably having sensors at the outside of the exposed surfaces. Sensors inside the model, though very impractical, can be done, but it's highly impractical. And most of the hotspots could actually be in the interior. And simulation actually helps you to do multiphysics type of capabilities. Basically here, that helps you not only to understand the electromagnetic field, but also the induced current and the temperature distribution due to this induced current. And now this temperature will cause thermal stresses, and one can actually keep on following the chain to actually visualize all the multiphysics properties using simulation. And finally, it's extremely important and very useful during early product development stage. This enables engineers and designers to test various design parameters right during their design phase, so that they can avoid costly prototyping and serious errors down the line. Now with this brief introduction, I'm going to quickly change gears here. I'm going to show you the product EMS, and we're going to have a very simple demonstration that highlights the electro-thermal capability of EMS. We're going to have we are going to design a custom coil which is used to heat, you've used for heat treatment, especially heating of a solid bar, as you see here. And some of the objectives of this simulation are the following. What kind of current, AC obviously, do I use? What is the value of the current, RMS value, for example? Do I have to pump through this particular coil so that I get a desired heating of the bar? And what is the temperature distribution inside the bar? How hot does my coil get? How hot does my bar get? What is the wattage or the loss in my bar? Okay, so these are some of the objectives of the simulation, and let us see how that is tackled using EMS. Okay, now I'm going to show you EMS. Okay, as you can see here, this is exactly as you saw in the picture a few seconds back. I have a custom-made coil that is designed using SolidWorks. I also have a bar that is placed inside the coil, and the objective is to understand what type of AC current that I need to pass through this particular coil, and how hot does my coil get and how hot does my bar get as a result of this excitation. Okay. Now, EMS is an add-in product inside SolidWorks, so it means that you do your design and simulation well inside the SolidWorks environment. Okay. Now, once you create your model, we are ready to do simulation inside what is called as an EMS tab. Okay. Every simulation in EMS is actually called as a study. So one can actually create a study inside EMS. I'm going to create a study here. You can give it a name, a meaningful name like 500 amps and 60 hertz. For example, because I'm going to subject an excitation of 500 amps RMS value of the current to this particular coil, and the frequency of excitation is 60 hertz. Obviously, this is AC current, so I'm going to have check AC magnetic here. We have to compute the circuit parameters, and here let's evaluate them at 60 hertz. Okay. Now EMS has several different simulations that are possible. I would say solvers that are possible. So obviously it comes with AC if your signal is AC. If your signal is DC or if you have permanent magnets in your design, you can use magnetostatic. If you have any other type of excitation like pulse or a rapidly varying excitation with time, you can resort to what is called as a transient magnet. Okay. And finally, we also have two more solvers. Electrostatic helps you to visualize the electric field in your domain, and electric conduction helps you to understand the resistance of complicated geometry. So these are the 5 types of solvers that come inside EMS. Okay. And as far as coupling is concerned, EMS has the capability to couple with thermal simulation, which is what we will do now. It also has the capability to couple with motion and structural. Okay. So when we define a study, this is what we do. So once you define a study, EMS actually generates or creates a study tree for you. Okay. Now this study tree might be very familiar for people who are well versed with SolidWorks. It's very similar to the SolidWorks study tree where you have different components. The simulation study tree is something extremely similar. Okay. Once the study is created, the next step involves defining what is called as materials. Okay. Now, for example, I have a coil here and I would like to assign it copper. So I go ahead and I apply materials, and EMS comes with a prepackaged material library that you see here on the right side of your screen that has all the commonly used materials. For example, it's got the conductor materials here, copper. It's got the properties that is used, thermal conductivity, electrical conductivity, etc., that are going to be used. So you use the copper and you go ahead and apply the material to the coil. The metal bar is made of a ferromagnetic substance. Let's call that mild steel. And there's one more component, which is the air. I'm just going to dwell a little bit on it once I start defining after I define the material. So let's call this air, and we're going to close it. Okay. Now let's spend a little bit time on the geometry of air and why it's important. So I'm going to go ahead first show the air geometry. Okay. Now, as you gentlemen and ladies, you know that the electromagnetic field not just exists in the coil, it does not just exist in the ferromagnetic substance, but it exists in the atmosphere all around us. Okay, and it's extremely critical to capture this magnetic field that's there in the air. So we do that by creating another geometry called air. Okay, and we assign that a material which is of air. Okay, so air has a relative permeability of 1, and it has a very, very low thermal conductivity. It's actually an extremely bad conductor of thermal as well as electricity. So we give it a very low conductivity value, electrical conductivity value. In fact, it's 0 here in the program, and it's very critical to have air in any type of electromagnetic type of simulation. Let's go ahead and hide the air geometry. Okay. Now, once you've defined the materials, the next step is to define what is called as the excitation. Okay. Now, as the study name indicates, we're going to have a study which has 500 amps, 60 hertz. Okay. So let's go ahead, define what is called as a coil. I'm going to define a solid coil. I'm going to select this as my coil, and I'm going to basically say where my current enters and where my current exits the coil, and then we define the RMS value of the current. In this case, it's 500 amps. This is an AC current, and I'm going to go ahead and say OK. So EMS actually has 2 types of coils. You have a solid coil if you want to define or model a coil, or if you just want to model a coil as an annular region, then you have what is called as a wound coil. When you define a wound coil, you define, in addition to selecting the coils, you also define the wire gauge of the wires involved, how many turns of wire that you use. Okay, so that's the difference between a solid coil and a wound coil. In a solid coil, you actually model the exact geometry of the coil. In the case of a wound coil, you don't model the coils, but you just model the area represented by, or the volume represented by these coils, and that's a wound coil. Okay, in this case, it's a custom-made coil. We are going to study how effective is the coil for heating purpose. Hence, we use what is called as a solid coil. Now, once the coil is defined, the next step involves finding out, the convection. Okay, so let's select here convection. I'm going to select the air geometry, and I'm going to tell the program that whatever surface is in contact with the air, be it from the coil or from the mild steel bar that you see in the middle, they're all convecting convecting to an ambient temperature of 300 Kelvin and at a very natural convection rate of 10 watt per meter squared Kelvin. Okay, so we define a convection. Once these are defined, we are ready to take a look, solve this problem. Okay, so EMS is a 3D finite element based simulation where everything depends on what is called as breaking the geometry into small finite elements. Okay, and these finite elements commonly are also referred to as mesh. Okay, so EMS has automatic mesh capability, so I can go ahead, I can create a mesh, and it has an automatic mesh generation feature which generates mesh for your model. Okay. So this is the automatic mesh generation tool in EMS. Let me go ahead and hide all my symbols here. Okay. So it as you see, it meshes the geometry. It basically breaks down the geometry into what is called as finite elements, and then the next step involved is solving this particular problem. Okay. So I'm going to go ahead and say run. Okay. So EMS actually has the ability to use multi-core processors while solving. So here I have a machine that is 4 cores, and it has almost 12 GB of RAM, and it's a i5 Intel core machine. And you notice that the solvers of EMS makes use of multi-core, and they're actually very fast, so that it enables us to solve these problems in real time. Okay, so once the solution is obtained, now it's time for us to take a look at the results. As you see here, we just solved this particular problem, and now we are ready to take a look at the results. Now, what are the kinds of results that one can look into EMS? Okay, and the first thing is the result table. A lot of results are organized inside the result table. For example, one of the things that we want to know for this coil is its inductance value. That's around 7.2 microhenries. Okay, so EMS first of all gives you the inductance of your coil, which is a very important parameter for design. It also gives you the flux linkage in terms of Weber, and finally it also gives you the losses both in the metal bar as well as the coil for this particular type of excitation. So the losses in the coil is very simple. It's I squared R, ohmic loss. You have a current going through it. There's also a resistance involved in the coil, and I squared R. But because this is AC current, you need to find out what is the AC resistance and the AC loss, the ohmic loss with respect to AC. So the program automatically calculates that. So that's now one thing to take care of, that EMS will be able to predict the skin effects and the AC effects. So the AC resistance and the loss here reflects the true loss and not just the DC loss. Okay. The next is the metal bar and the amount of wattage lost in the bar. And as you noticed here, we never applied any current to the metal bar. What's happening here is the AC current in the coil is actually inducing a current in the steel, and this causes heating of the steel, and this is the wattage that is responsible for heating the particular steel. And you can also compute the resistance of the coil. That's also computed here. Note that this is the AC resistance and so on. Now the result table organizes all the engineering quantities, and one can also view plots in a 3D space. Okay, so first one can take a look at the magnetic flux density in my model in Teslas. Okay, so now I have several options as far as post-processing is concerned. I can take a look at inside my model the values of magnetic flux density and the distribution inside my model through what is called as a section plot. Okay. Now here I can not only look at the values at the surface but also inside my model, and I can go ahead and do what is called as a probing. So here I can select locations in my model. In this case, I'm selecting locations in my section, etc., to get the value of the flux density. So notice here that you really have infinite number of sensors available to you once you solve this particular problem in a computer. Whereas in real life, you're basically limited by a few sensors that you put in before you do this experiment. The next thing that EMS does for you is what is called as a vector plot. Okay, so the same magnetic flux density, not just as a continuous plot, but also as vectors. So one can take a look at it. Now here you notice the flux density that is developed inside the bar, okay, is actually visualized as a vector. Okay, notice that all the while I have not turned on the air geometry, so I can, for the first time, I'm going to go ahead and show the air geometry, and you can actually see not just the results, the vectors in the solids, but one can also take a look at the vectors in the air geometry as well. So here you can see the maximum flux is all around the bar, which is what we want. We want all the flux change to happen in the bar that causes the heating of the bar, and there's very little flux in the air around. Okay, in this case. Let me go ahead and turn off the air here. Now we saw section plot and vector plot. Another important quantity is also the ability to look at values within a particular range. Okay, so we'll do that for a different plot. Now let's look at the temperature plot. Okay, now here I can take a look at my temperature. So this is the distribution of temperature. Notice that it doesn't really get too hot beyond 300 Kelvin. So the maximum temperature is around 330 Kelvin, and the minimum is around 311 Kelvin. Okay. Now we know that the coil is going to get hot because you're going to send some current through it. But to be able to understand how hot the bar gets, one can actually isolate. So here I choose to plot only on my bar. Okay, and then let me pick a scale that is more familiar, maybe a Fahrenheit or Celsius here. And now this can pretty much give you the temperature distribution only on my bar, the maximum and minimum reflecting the ones that is only shown on the screen. Okay, so about 100 Fahrenheit or 102 Fahrenheit is the temperature rise in the bar because of my 500 amps current. Okay, obviously that's not something that I'm looking for. I want to heat it much beyond that. I want to heat it, you know, I'm from Canada and I like to look at units in Celsius. So let me go ahead and just convert this. So what we have is a heating of around 39 degrees Celsius. Okay, the ambient is around 27, so we really have just heated it a little bit. Okay, suppose I want to heat it to about 100 degrees Celsius. What kind of current should I need to pump in? Is a question that needs to be asked. Okay, so I've done various simulations here at various currents. So let's take a look at how they compare. So I'm going to go ahead and compare all the studies. Let me remove the 1000 hertz case. So I've got 100, 1500, 2000 and 500 amps. What happens when I do all these four cases at 60 hertz? Okay. One thing you can do is you can compare the loss, the loss in the metal bar, and you can actually plot it. So basically this is the loss in the metal bar when you take the various studies into consideration. So I have these values here. So when I have about 1000 amps, so my loss is around 17.5 watts. If I have 1500 amps, my loss is 39 watts. Okay. Notice that it's not really linear. Okay, I double the current, but I don't get 2 times the loss. I get much more than that. When I have 2000 amps, I have close to 69 or almost 70 watts. Okay, and with 500 amps, obviously I've got only about close to 4.5 or 5 watts of loss here. So obviously with 2000 amps, I'm really going to get a very high heating temperature distribution in my bar, so that basically will help me heat this particular rod. Okay, so I'm going to go ahead and close this, and let's go to a situation where I have 2000 amps current going through this. Okay, and I can go ahead and take a look at the temperature. Notice here that it gets heated to around 215 degrees Celsius is the maximum temperature that I get in my bar. There's a gradient obviously, so the minimum temperature in my bar is around 203 degrees Celsius, and the maximum is around 215 degrees Celsius. Okay, and the coil with its particular geometry is capable of making such type of heating with an AC current of 2000 amps and 60 hertz. Obviously, a lot of effects can be studied. So what happens if I change my frequency of excitation from 60 hertz to say 1000 hertz? Okay, so that is also certainly possible from 60 hertz to 1000 hertz. We did that simulation here as well. So what happens when I have 1000 amps and 1000 hertz and 1000 amps and 60 hertz? So one can actually do this comparison. So I just take the three things that are relevant, and again take a look at the losses, and I'm going to go ahead and compare. Okay. So obviously, when I increase the frequency, I'm going to get more loss, ohmic loss out there. Okay, at 1000 hertz, I get close to 20 watts of loss, and at 60 hertz, I get around 17.5. So it's the same current, but you can now study the effect of high frequency AC on the heating. Okay, and so you can determine whether you want to increase the frequency versus increasing the current, and these kind of studies can be done. Okay. Now another thing that I wanted to show you is what is called as an isoplot. And now this helps you to understand critical areas of the model. For example, an isoplot helps you to find out the areas that are, say, above a certain value. For example, I would like to understand areas that are about 180 degrees Celsius, and here and I can go ahead, reduce, increase, and so on. Okay. So an isoplot basically helps you to understand areas above or below a particular value. Okay. So here the minimum was 203. So if I want to find out all areas above 210 degrees Celsius, so I just set the value 210, and this much of my component or the bar is about 210. So the isoplot basically helps you to identify regions. So for example, if you want something that's over 213 degrees Celsius, it's only this part. So all critical areas in your model can be examined using isoplot. An isoplot can be used with temperature, it can be used with magnetic flux, it can be used with field intensity, and any of these. Okay. Lastly, I want to show you what is called as the automatic report feature inside EMS. Okay. So one can generate a report inside EMS, either in Microsoft Word form or in HTML form. And here I can specify what are the properties that I want to see. I can take a look at the ones that I want, for example, temperature I want, and so on. So when you do that, when you create a report and say OK, EMS automatically captures all the simulation data that you did, the pre-processing data, the post-processing data, the result tables data, the data about your materials, etc. And it automatically generates a Microsoft Word report inside SolidWorks. So I can actually go ahead, because this is Microsoft Word, I can go ahead and edit this information. So and it pretty much has everything that I need. Okay, all the plots are there. It's stored along with the geometry, and this is good to record or tabulate and take notes for your simulation and so on. Also useful for design review meetings and so on. All right, with this pretty much we come to the end of this particular demonstration, product demonstration, but we still have some more presentation slides to go on. Okay. At this point, I would like to go on to products and bundles, and I would like to invite my colleague, Mr. Rick Seidler, would make him the presentation as a presenter, and Rick, it's all yours, and he will be going through the product bundles, applications, and throughout the rest of this presentation.
Arvind, thank you very much. Hello, everybody. My name is Rick Seidler. I'm the account manager for your area, and just want to go over the product bundles a little bit with you. What Arvind showed you today is our EMS product, and the EMS product comes in two flavors, let's say, two bundles, and those are the first two boxes starting at the left-hand side. What he was demonstrating is the EMS Professional, and then as an add-on to that, he added the thermal module. So he coupled it to thermal analysis. Other things that you can do as far as add-on modules is you can add on a motion analysis module. Pretty soon, coming out this year yet, we're going to have a structural analysis solver to couple that to the electromagnetic. And then also we have a network license capability if you'd like to add that on. The other bundle of EMS that we have is called EMS Premium. And this is a package that just adds the thermal and the motion to it. And there's a better price point for getting it all at one time. The last block on the right is another product that we also carry for high frequency type applications. RF components or microwave. If you have any type of applications for that, we also offer that type of a product too. And one thing I did want to mention here, as an attendee today, we certainly appreciate your time and just want to throw out that if you decide that this product is a good fit for you and you place an order by the end of October, I will discount the price of that package 20%. Okay, and that is for you attending today. So I want to pass that on. Arvin, do you want to just flip the screen one? Okay, this screen here, what I want to show you here is just the different application areas. Arvin showed you one particular area today, but if you look at this screen and pretty much everything to the left of the vertical line between electronic design and electromagnetic, electromechanical design is available to you in the EMS software. Okay, so whether you're dealing with motors, coils, magnets, MEMS, you name it. Excuse me a second. You'd be able to do that type of application with the EMS program. And then what I also have down here are the key industries where the product is being purchased. Just a lot of different type of industries, folks using this software to get their jobs done. Okay, over on the right is pretty much the, again, that high frequency product we have called HFWorks. All right, go ahead, Arvin. You want to flip that? Okay, so as far as today's demonstration, what you would need is first you need the SolidWorks CAD system, because one of the big things about our product is we run right inside SolidWorks, making the product very easy to use. It takes a lot less time to do things because you don't have to be involved with doing transfers of files all the time, from the CAD system out to the electromagnetic software. And then, so in addition to SolidWorks, you would then need the EMS Professional with the thermal add-on. And you'd be ready to go and start doing these applications. Now, at this point, what I want you to know also is I recorded this session today. If I did a good job of recording it, it's going to come out nicely. And what I'm going to do is email it to all of you so that if you want to share this with anybody else at your company that you think would benefit from seeing it, that'll be available to you. Lastly, again, I want to thank you for coming out today. And then I think you might know this, but just in case, emworks.com, that's our website. You can go on there. There's a tab called Success. And under that, you're going to find a lot of white papers. Also up on the right-hand side, there's an arrow that will take you to our YouTube channel where you see a lot of video presentations. And then lastly, for sales, it's sales@emworks.com. In particular, I'm going to just throw out my phone number if you just want to jot this down, although I'm going to be sending you an email. My number directly is 724-510-0204. And that's it for today, except we can open the floor up to any questions. If anybody would like to just go ahead and type in the chat box, it looks like there are some questions. So I'll pass this back on over to Arvin. And Arvin, if you want to go ahead and answer the questions.
Yep. Muted. Thank you very much. We have a question. Is it possible to do high frequency microwave range simulations? Yes, the answer is yes, but then you would need a package called HFWorks, as Rick mentioned earlier. So for all information about HFWorks, please feel free to contact Rick, and we will be happy to show you things regarding HFWorks. Okay. So yes, this software is suitable for high frequency simulations. Okay.
Unmuted.
In fact, in the case of the high frequency application, if you do decide that that's something that you'd like to see, we could actually set up a one-on-one demonstration to show you the HFWorks product.
All right, we'll just wait if some more questions crop up.
See, I see another one here, Arvind. Is it possible to do thermal simulations in HFWorks?
Yes, it is possible to do thermal simulations in HFWorks, and it's best answered in a different forum with just HFWorks, where it's a different audience. Yes, we'll be happy to help you with that later. Okay, if we have no more questions at this moment, Rick and I would like to thank you all for.
Hold on a second, Arvind. Looks
Okay,
like
there's one more question. Can we use thermal simulation for electrostatic study? The answer is yes, you can use thermal simulation for electrostatic studies. It's the same way you can couple it to thermal. So when you create an electrostatic study, just like how you created this AC, you have to couple that to thermal, and then you will be able to get the thermal results.
that looks like that might be all the questions.
Okay. Well, we thank you all for attending today's demonstration. I hope this was useful for us, and should you have any questions, feel free to contact us in the information that was provided, and we look forward to hearing from you and trying to answer your questions if you have them in the future. Okay. With that, we will sign off right now and wish you a great day today. Bye-bye.
Yes, thank you very much, folks.